Welcome to practice exam 2B. Okay, here we have a little Le Chatelier's principle gauntlet of destiny. So we need to analyze how adding in or changing the reaction conditions is going to shift this reaction. First thing I would like to do is point out, so it says this is an exothermic reaction. So that means we're going to be treating heat like a product because the reaction will give off heat as it proceeds. Okay, with that in mind, let's go through and see how each of these will affect reaction. First, it says more O2 is added. So if we're adding in O2, which is a gaseous reactant, if we increase the product, or if we increase the amount of reactants, that means that if this is at equilibrium, suddenly we have we have too many reactants and we need to shift to the right to make more products. So adding in a gaseous or aqueous reactant will shift the reaction to the right. If we added in a product, it would shift it to the left. So this is going to create a shift to the right. Okay. So next we have more C6H12O6, so more sugar is added. Now the thing to point out here is, if we look at this, what is the phase of matter we're looking at? It's a solid. Remember, solids and liquids do not create shifts with Le Chatelier's principle. So that's all well and good. This is still going to result in no shift. Okay, up next we have the volume of the reaction vessel is increased. So what would happen if we had a system, and so let's consider a box where our reaction is taking place. And there's our vessel, and let's just throw in a few particles in here. Say these are the molecules of gas bouncing around. So what happens to the pressure if we take this vessel and suddenly we make it much larger? What's going to happen to the pressure? Well, there's going to be fewer collisions because the gases have more space to move around, right? So if we do this, that means that this is going to cause the pressure to drop. So our pressure is going to go down in this scenario. Le Chatelier's principle states that if a system involving gases is at equilibrium, it's got the ideal partial pressure product to reactant ratio, it's all good, and then suddenly what we did here was we made the pressure plummet. We made it drop by increasing the volume. So Le Chatelier's principle says that the reaction is going to shift to the side of the reaction that's going to help make up for that plummet in pressure. So if we consider how many moles there are on each side of the reaction, there are 6 moles of gas in the reactants, and we're only considering gas because gas is what contributes to pressure. We have 12 moles of gas in the products. So since we made the pressure drop by increasing the volume, this reaction is going to shift toward the side that corresponds with more pressure. So that means the reaction is going to shift to the right because 12 moles of gas corresponds to more pressure, in fact, twice as much pressure as 6 moles of gas would. So by shifting to the right, this is going to allow the reaction to help build up the pressure again. Now, if we decrease the size of the reaction vessel, if we made it smaller and caused the pressure to increase, then the reaction would shift to the side with fewer moles of gas. The next one says we're removing H2o gas. So if we're getting rid of products, we were at the ideal product-to-reactant ratio. Suddenly we don't have enough products. The reaction is going to need to shift to the right in order to make up for us losing the products there. So once again, we're going to have another shift to the right. Then finally, we're dealing with temperature. What happens if the temperature is increased? Now, a simplification of thermodynamics here, but it's one that works really well. So because this is exothermic, we said that heat we can treat like a product. And so we're going to do this the exact same way we would treat any other product. If we increase the heat, that means the reaction is going to shift to the left to compensate. So finally, we have shift left here. So this problem includes basically all 3 scenarios that we can encounter with Le Chatelier's principle. What happens if we change the concentrations of either aqueous species or gaseous species? What happens if we change the temperature? And what happens if we manipulate the pressures by changing the volume of the reaction vessel? All right, in this problem, we're trying to figure out in which of these cases the entropy change is going to be positive. Okay, so there's basically 2 main criteria that we're going to analyze when looking at a reaction. First, phases. So if we think about molecules and phases of matter, solids are the most ordered. They have the least inherent entropy. If we melt them and we get a liquid, liquids have greater entropy. And then if we evaporate liquid and we get a gas, well, that has the most entropy of all. Also, if we go from a solid to a gas, so if we go through sublimation, that's also going to be a notable increase in entropy. The other thing that we're going to look for, going from fewer moles of reactants to more moles of products tends to lead to an increase in entropy, because now if we're breaking them into more particles, there's more freedom of movement, there's more possible microstates, there's more ways they can orient themselves with respect to each other. So we're going to look for a reaction that gives us at least one of these two changes, and that's going to be choice C here, because notice that we're going from 1 mole of a solid reactant to 2 moles of products, one of which is a solid and one of which is a gas. So it actually checks both of these boxes right over here. Ding, ding. Not literal boxes, but anywho. Okay, in this problem, we're looking to see which one has the greatest gas phase entropy. And all of these are atomic gases. They're noble gases. So remember, greater temperature means greater entropy. So we look through here. We can eliminate a few of these choices, the ones that are at 1000 Kelvin. Now we're choosing between helium, argon, and radon. So of these, we're going to pick the heaviest. So if we're just comparing different atoms, we're going to go with the one that is the heaviest. So if we look at the periodic table, we'll see that radon is far heavier than argon, which is far heavier than helium. Because the heavier the atoms that we're looking at, the more shells of electrons they have, the more shells of electrons they have, the more microstates they have, etc., etc., etc. In this question, we're trying to figure out which of these processes can perform work on the surroundings. AKA, we're looking for a reaction that is spontaneous, because a spontaneous reaction can perform work. So let's go through each of these. Choice A, freezing water at 25 degrees Celsius. So is that spontaneous or non-spontaneous? Well, if it was below 0 degrees Celsius, which is the freezing point, it would be spontaneous, but no, this one not so much. At 25 degrees Celsius, water tends to be a liquid. We would have to put in work in order to freeze it. Combustion of methane. I like that answer. The combustion of hydrocarbons, molecules containing carbon and hydrogen, and things like carbohydrates, which have carbon, hydrogen, and oxygen, lead to their exothermic reactions, and they lead to an increase in entropy. This is a perfect storm for a spontaneous reaction. So combustion of hydrocarbons, such as methane, is going to be spontaneous and can do work. In fact, a common example of the combustion of methane, things like the catabuses. So they are powered off of natural gas, which is methane, and the combustion of it allows them to, well, move around, do work, go from place A to place B. Okay, so assembling a jigsaw puzzle, no, we would need to, that's kind of a silly answer. We would need to put in work to do that. The next one is boiling water at 373 Kelvin. So this is the boiling point. Well, technically the boiling point is 373.15 Kelvin. But we're at the boiling point here, which means this process is non-spontaneous in either direction. It's an equilibrium process. So we're going to eliminate this choice. And then finally, carrying a rock from the bottom to the top of a hill. No, that's just doing labor. So no, not so much. Only choice B. All right, in this problem, we have to come up with an equilibrium expression. So I have aqueous things. So I'm just going to write this out as Kc for concentration, since aqueous species do not exert pressure. Okay, so we're going to do products over reactants, and we're only going to include anything that is either aqueous or gas. In this case, there are no gases, so it's going to be the concentration of this aluminum sulfate. And there is no coefficient in front of it, so it's just going to be to the first. We're not going to include the manganese in our expression because, hark, it is a solid. So products over reactants. Not going to include the aluminum because, once again, solid alert, solid alert. But we are going to include manganese sulfate. So that's going to be MnSO4. And we're going to raise it to its coefficient. So its coefficient, we can see here, it's 3 in front of it. So I'm just going to make this to the third power. And we are good to go. So the answer is going to be choice C. In this problem, we're tasked with relating the equilibrium constant. So we're given the Keq, which is 0.0150, and we're relating that to rate constant. So an important relationship that we have is an equilibrium constant is equal to the rate constant of the forward reaction divided by the rate constant of the reverse reaction. So, very, very cool. Let's see what we have here. We know what the equilibrium constant is. We are given that in our problem stem. So we have this. We know the forward reaction has a rate constant of 0.0693, so we know that, which means what can we solve for? Well, that. So let's do just that. Let's plug in our values. Okay, there we have our values. So let's multiply the Kr through. There we go. Now we're going to divide both sides by our Keq, or 0.0150, like so. And when we do, we'll solve for Kr, which is equal to 4.62 seconds to -1. Okay, we're almost there, but now we need to translate this into a half-life. Now, the problem should have specified that the reaction was first order in both directions because we need to know what order it is in order to use the right equation. So here we have our equation. Half-life for a first-order reaction is 0.693 divided by the rate constant K. So let's plug in that rate constant. Now there we go. And we'll end up getting that our half-life for the reverse reaction is equal to 0.15 seconds. Okay, in this problem, we're looking at a very important reaction for our bodies. So energy is stored in ATP in the form of these high-energy bonds that when we dissociate to form ADP, adenosine diphosphate, and a phosphate, a lot of energy is released, and this energy can be harnessed to do other processes. So, what we're trying to do here is relate the free energy change with what? Well, Keq. So, is there an equation for that? You bet there is. And it's right here. The standard free energy change of a reaction, delta G standard, is equal to negative RT times the natural log of Keq. This is what we're going to use to relate our equilibrium constant, which we're trying to find, with our delta G standard, which we're given. So let's plug in our values. We have negative 30.5 kilojoules per mole. Now we want to make sure that we're plugging in, since I plugged in kilojoules here, you can either plug in joules or kilojoules. Just need to make sure that you're using appropriate units in your gas constant R. So there we have 0.008314 kilojoules per mole Kelvin. Our temperature, we're told this is at 37 degrees Celsius, so we're going to make sure we plug in our absolute temperature. So we're going to add 273 to that and get a temperature of 310 Kelvin. Voila. And then times the natural log of Keq, which is what we're trying to solve for here. So we're going to divide both sides by negative RT. So end up getting that the natural log of Keq is equal to 11.83, and then to get rid of that natural log, we're going to do e to both powers, and let's see what we end up getting. 1.38 times 10 to the 5th. Okay, here we have another Le Chatelier's principle question. This is an exothermic reaction, so I'm going to treat heat as a product. It's a nice simplification from thermodynamics that we can do here. Okay, and now we want to see what each of these factors does to change the concentration of NO2. So the first one says increase the temperature. If we increase the temperature, it's like we're adding products, so this reaction would shift to the left. So if it's shifting to the left, what happens to the concentration of NO2? Well, the NO2 concentration would go down. Okay, so I'm just going to mark this in here next to the box where it says increase the temperature. I'm going to write it down. Okay, now let's do the other ones. The next one says increase the pressure of nitric oxide. So this is a gas. If we add more reactants, it's going to shift to the right. If it's shifting to the right, that means we're going to make more products, more of the NO2. So this is going to increase the amount of NO2 present. And then finally, we have decrease the amount of NO3. If we do that, the reaction will need to shift to the left in order to compensate for the reactants that we lost, which means the NO2 would go down. So we're looking for decreases, increases, decreases, and that's going to be choice E is the one that has all the relationships correct here. Okay, in this question, we want to find out at what temperature this reaction becomes spontaneous. So we're trying to relate, well, we can see it in our table O data. We're trying to relate enthalpy and entropy and spontaneity, which we can use these to find, to relate them to free energy in order to do so. So the equation that relates enthalpy, entropy, and free energy is our friend, delta G equals delta H minus T delta S. But first, we actually have a little bit of a task that we need to do because we're given, so we can see here in our table O data, we're given thermodynamic information for these individual molecules. We need to find the enthalpy and entropy change of the reaction. So whenever we want to do that, we need to use the ever-powerful products minus reactants rule. So let's first figure out the enthalpy change of the reaction and the entropy change of the reaction. And I like to offset the products and reactants in brackets, so the enthalpy change of this reaction is going to be equal to, so notice that there are 2 moles of NO. So I'm going to take the enthalpy of formation of NO, which is this value right here. We're going to multiply it by 2, so there's 2 moles of it. And we're told here that it is a cool 90.25 kilojoules for every mole. Okay, so there we have our products minus reactants. So our reactants, we can see, well, these are really exciting values that we've got here. We've got 1 mole of nitrogen, but its enthalpy of formation is 0. And we've got 1 mole of oxygen. Again, it's standard elemental state. So that means when it's all said and done, well, this whole thing totals 0. Neat. So our enthalpy change is 180.5 kilojoules. All right, we've got that part down. Now let's find the entropy change of this reaction. Once again, we're going to use the products minus reactants rule. So our product, we have 2 NOs, so there's 2 mole of NO, and this clocks in at 210.8 joules per mole Kelvin. Sorry, it's hard to see what that says there. It says joules per mole Kelvin. There are our products. So minus reactants, and here we have the values tabulated for those. So it's 191.6. We've got 1 mole of N2. Again, it's 191.6 joules per mole Kelvin. And to that, we're going to add, we've got 1 mole of oxygen, and the oxygen is 205 joules per mole Kelvin. Okay, so now let's see what we end up getting for the entropy change. So it ends up being 25 joules per Kelvin. Now, just keep in mind, as we proceed forward, this is in joules per Kelvin, whereas our enthalpy is in kilojoules. We can proceed using joules or kilojoules as long as we're consistent with our units. So now our strategy. We have our delta H of the reaction. We have our delta S of the reaction. Whenever you want to find out at what temperature a reaction goes from spontaneous to non-spontaneous or vice versa, the key is, well, think about this. If a reaction is spontaneous, what do we know about delta G? It must be negative, right? If a reaction is non-spontaneous, that means that delta G must be positive. So what's the magic number where a reaction goes from spontaneous to non-spontaneous or vice versa? It's where delta G equals 0. So we're going to set delta G equal to 0 and solve for the temperature. So let's do just that and see what we end up getting. Okay, so I just moved around our thermodynamic data and got rid of the products minus reactants just to make a little bit more room here. Now let's solve. So we have 0 is equal to our 180.5 kilojoules minus T, which is what we're solving for, and then delta S. I'm going to convert delta S into kilojoules per Kelvin because I prefer to work in kilojoules. So I'm going to divide this number over here by 1,000, or 1,000 joules in 1 kilojoule. So we'll get 0.025 kilojoules per Kelvin. Add T delta S to both sides. Rearrange. So we get this. Now we're going to divide both sides by delta S. And when we do this, kilojoules cancels out and Kelvin's in the denominator of the denominator, so it's going to flip to the numerator. And what we're going to end up with is 7,220 Kelvin, which when we subtract 273 from that and turn this into Celsius, this ends up equaling 6,947 degrees Celsius, which doesn't match our answer exactly. Probably just a discrepancy in the number of sig figs used, but pretty dang close. And in case you're wondering, this reaction becomes spontaneous around lightning strikes. So lightning strikes are hot enough to turn nitrogen and oxygen gas in our atmosphere into nitric oxide. All right, this question tasks us with making some assertions about what's happening at point A, which is marked here. So in terms of point A, we can see here, one of the most important points to be able to recognize on a graph like this is this free energy well right here, this minima. So what exactly does this minima represent? What chemical state? It represents equilibrium. So a reaction will travel until it gets to, not travel, but will proceed until it gets to this ideal product-to-reactant ratio. So the most thermodynamically favorable product-to-reactant ratio known as equilibrium. So we can have too many reactants, in which case we'll have to make products. We can have too many products, in which case we'll have to make more reactants. Or if everything's just right and Q equals K, then we're at equilibrium. So what's the deal then with point A right here? So notice how point A, we're situated more toward the products than the reactants. And specifically, most importantly, we're past that equilibrium point. This means that we have too many products at this point. So this means that Q, the product-to-reactant ratio that we want, or that we have, rather, is greater than Keq, the product-to-reactant ratio that we want, that the chemical reaction is going to eventually settle at. So if Q is greater than K, that always means that there are too many products, and the reaction would have to proceed to the left then in order to make more reactants to get to equilibrium. Or if we visualize it on the graph, we'll need to make more reactants so we can eventually settle in at equilibrium. So with that in mind, let's look at what these statements say. So statement 1, Q is less than K at this point. No, Q is greater than K. The product-to-reactant ratio that we have is greater than the product-to-reactant ratio that we want. So I'm going to just cross that out. Delta G standard is less than 0. Okay. So delta G standard is the energy difference of pure products minus pure reactants. So the products minus reactants rule, which means delta G standard is represented by this arrow right here. As we can see, this is a negative value. The products are lower in free energy than the reactants. So this is indeed a negative value. So delta G standard is indeed negative. I like that one. The next statement says more products must be produced to reach equilibrium. No, we already have too many products. Too many products. We need to make more reactants to reach equilibrium. And then finally, the process of moving from equilibrium to point A would have a positive delta G. So if we were at equilibrium, at this point right here, and we wanted to get up to point A, Well, if we're at equilibrium and we want to go either direction, that's going to require energy because equilibrium is the ideal product-to-reactant ratio. So indeed, we would have to put in energy to get up to point A. So this last statement here is true as well. Anytime you want to move away from equilibrium, that's always going to be a positive delta G. So 2 and 4 are the correct statements here. This question asks, which of the following reactions at equilibrium will not be affected when the volume of the container is decreased? So recall that when we change the container volume, so let's say we go from this, here's our box with some particles in it, to this, or vice versa. So we could really think about this either direction. If we take a container and we increase the volume, that's going to cause the pressure to drop. So the Chatelier's principle says that a reaction that involves gaseous species, when it's at equilibrium, will have an ideal product-to-reactant partial pressure ratio. If we increase the volume and we cause the pressure to drop, the reaction is going to shift to the side of the reaction that allows us to have more pressure to help make up for that loss. Or vice versa, if we shrink a container, then the pressure would go up. And Le Chatelier's principle says that the reaction would shift in order to help lower the pressure then. So we can look at our reactions. And for example, this first one, if we look at both sides of the reaction, there are 2 moles of gas on the reactants and 2 moles of gas in the products. So both sides correspond to the same amount of pressure. So shifting to the left or to the right is not going to do anything to help compensate for a pressure change. So this will not be affected because there's no benefit to shifting either direction. So this one is going to be one of them. If we look at our next one, we have 3 moles of gas versus, 0 moles of gas over on this side. So if we change the volume, it will indeed shift. So this one will be affected when the volume of the container is decreased. And then finally, this last one, we have 2 moles of gas here and 2 moles of gas here, which means equal number of moles of gas on both sides. Not going to shift either direction because neither direction corresponds to more or less pressure. So 1 and 3 will be the ones that are unaffected by changing the volume. And this says will be unaffected when the container is decreased, but the same question, it would be the same question if it said which one will be unaffected if the volume of the container is increased. Okay, in this question, we're asked to find Kp, and we're given a bunch of information about equilibrium partial pressures. So we're told that it's allowed to equilibrate, and these are the values that we observe at equilibrium. So we're already given the equilibrium partial pressures. All we need to do is plug these into our equilibrium expression. So let's write out that equilibrium expression right now. So Kp is equal to the partial pressures of the products. So pressure of SO3 to their respective coefficients over reactants, so the pressure of SO2, and that's going to be squared, times the partial pressure of oxygen. That's a coefficient of 1, so we don't need to do anything there. Now let's plug in our values. We have 0.30 atmospheres of our SO3 over, and for SO2, we're told that it's 0.25 at equilibrium. So 0.25 squared. And then for oxygen, the oxygen is at a cool 0.45. Okay, let's do our calculation and see what we end up getting. 3.2 for the win. This question, we're looking at an exothermic Haber process. So we're trying to see which way the reaction will shift if we change conditions. We're looking at Le Chatelier's principle problem. And again, I always like, if I ever see exothermic, the first thing I do on these problems is I include heat as a product if this is an exothermic reaction, or heat as a reactant if it's endothermic. All right, let's go through these. What will happen if question or statement 1 says we decrease the pressure, or decrease the volume, of the reaction vessel? So if we decrease the volume, what's going to happen to the pressure? So same amount of gas in a smaller space, this is going to cause an increase in pressure. So Le Chatelier's principle states that the reaction is going to shift to undo that increase in pressure, which means if we look at 4 moles of gas in the reactants and 2 moles of gas in the products, it's going to shift to the side with fewer moles of gas. That'll help alleviate some of the pressure. So this will make the reaction shift to the right to make more products. So 1, yes indeedy. Ding! Okay, if we increase the temperature, it's like adding a product, a bit of a simplification of thermodynamics, but one that works really well for predicting Le Chatelier's principle shifts. So if we increase products, it's going to shift toward reactants. That's not what we want to do here. The next one says removing NH3 from the reaction mixture. So if we were removing products, then this is going to shift to the right and make more products, and then we can remove even more. So we can distill out the NH3 to make the reaction shift and keep making more NH3. This is going to be effective, so I'm going to give this a ding. And then finally, we have decreased the partial pressure of N2. Removing reactants is going to cause the reaction to shift to the left, which is not what we're trying to do here. So of these, 1 and 3 only are going to shift the reaction to the right. This question tasks us with finding in which of these reactions does Kp equal Kc. So recall that the relationship between Kp and Kc is that a la Pivnert, Kp is equal to Kc times RT to the power of delta N, where delta N is equal to the moles of gas in the products minus the moles of gas in the reactants. So it's the change in the moles of gas. Okay, so if we want Kp to equal Kc, that means that we want this whole RT delta N, that means we want this whole RT delta N to be equal to 1, right? And what is the easiest way to get that to equal 1? Well, it is to make delta N equal 0. Because if it's equal to 0, any number to the 0th power is 1, and that will effectively cancel out this RT delta N term. So, in which of these cases is the delta N equal to 0? In the first one, so delta N is equal to, there's 3 moles of gas in the products minus 2 in the reactants, so this is 1, not what we're looking for. In the second one, we've got 4 moles of gas in the products and 0 moles of gas in the reactants, so in this case, delta N is 3. In the next one, we have 0 moles of gas in the products minus 3 moles of gas in the reactants, so it's negative 3. In D, we have 2 moles of gas in the products and 2 moles of gas in the reactants. Hey, guess what? We've done it. We now have our answer. Okay, in this problem, we're looking at a reaction called the pillar of salt, where we're forming this solid sodium acetate. So, we're looking for the delta G of this particular reaction under these particular conditions. And notice here that we're given concentrations that are decidedly not 1 molar. Anytime we're trying to find delta G under non-standard concentrations, anything other than 1 molar, we're going to have to use the equation delta G equals delta G standard plus RT times the natural log of Q. So Q is certainly something that we can find here. We can find the product-reactant ratio given these concentrations, but we're left with a subsequent issue, and that is, well, we don't know delta G standard. Or do we? For we're given Keq here. Remember, if you know Keq, you can find delta G standard. And if you know delta G standard, you can find Keq. So we're going to do that by using the equation delta G standard equals negative RT times the natural log of Keq. So basically, this is a 2-part question. Our first goal is to figure out delta G standard. And then once we know delta G standard, we can solve for delta G. So first, let's find that delta G standard. So let's plug in our values. Our R is our classic gas constant, 0.008314 kilojoules per mole Kelvin, classic. Temperature is 298 K. That we got from right here. And then finally, we have the natural log of Keq, which is 0.004. So when it's all said and done, we end up getting, well, Kelvin cancels out, and we'll end up getting the delta G standard is equal to 13.7 kilojoules per mole. Whoa, we're halfway there. But not quite done yet, because we're not looking for delta G standard, which is what we just found. We're looking for delta G. So we're going to need to use this information in Q to find our delta G. So let's just find Q first. Let's write an expression for Q. So Q is equal to products over reactants. And, well, our product is a solid, so we're just going to plug in 1 for that. In our reactants, we have H+, and we have acetate, CH3COO-. So here's our expression. Let's plug in our values, like so. And we'll end up getting that Q is equal to 0.0025. Now we have everything we need to plug into our equation here and solve for our actual delta G under these non-standard concentrations. So let's plug in. Delta G is equal to our delta G standard. We solved for that already, 13.7 kilojoules per mole, plus R, 0.008314 kilojoules per mole Kelvin, times T, which again is 298 K, times the natural log of Q, which as we solved for right here is 0.0025. Let's see what we get. So this whole thing here ends up equaling negative 14.8 kilojoules per mole. So then we'll add that to our delta G standard and get our answer of delta G equals negative 1.1 kilojoules per mole. In this problem, we need to manipulate two different reactions and somehow combine them to get an overall reaction, which is what we see right here. The first thing I always like to do is I like to see if in our reactions that we're looking at, so reaction 1 and 2, if the reactants and products are on the correct side, where we're trying to find them in our overall reaction right here. So, if we look at reaction 1, we'll see that A is a reactant and B is also a reactant. Well, in the reaction that we're striving for, A and B are both reactants. So I think in terms of what side of the reaction they're on, this one is good so far. We might need to play around with the coefficients, but for right now, the reactants and products are where they should be. Now, if we look at reaction 2, notice that D is a reactant here, but we want D to actually be a product. So that means that we're probably going to have to flip this reaction around, and that's exactly what we're going to do. So I'm going to call it reaction 2 prime, and I'm just going to flip around this reaction, so it's going to become C plus 2B yields 3D. And whenever we do that, so the K for this, I'm going to call it K2 prime, since we flipped it. If we reverse a reaction, so the reactants become the products and the products become the reactants, what do we do to the value of K? Well, we take the inverse of it, so it's going to be 1 over 15. So K2 was 15, so we're just taking the inverse of this. So now let's take a look again at reaction 1. And actually, to simplify this now, just to help there be less moving parts, I'm going to cross this out. We don't need this anymore because we came up with reaction 2 prime. This way, just kind of like doing a little bookkeeping here. Okay, so if we add in reaction 1 the way it's written, so notice that the way it's written, we have 2A and 2B becoming 2C. Well, there's a problem here because in our overall reaction, we only want 1 mole of A. So what I'm going to do to help make this match up is I'm going to cut all the coefficients in half. So I'm going to call this reaction 1 prime, and all we're going to do is cut everything here by 1/2. So it's just going to be A plus B yields C. And whenever you cut the coefficients in half, all you have to do to the Keq, so I'm going to call this K1 prime, is, so K1 was 4, we just have to take this to the 1/2 power. So anytime you manipulate the coefficients, by whatever factor you change them by, you take Keq to that power, you raise it to that power. Since I cut them in half, I'm taking it to the 1/2 power here. So the square root of 4 is equal to 2. And again, I'm going to cross this out because we have a new and improved reaction that will be of more use to us. So the final thing that we're going to do is, if we combine these together as they are, let's see if anything cancels out. So we can see that C appears both on the reactants and the product side, 1-to-1 ratio. Those will cancel out. And if we look at B, there's 1B in reaction 1 prime, and there's 2B in reaction 2 prime. So we're just going to add those together, and we'll get our overall reaction of A plus 3B yields 3D. Now, wait a minute. Where does that look familiar from? This seems familiar. Wait a minute. Hark. It's the reaction that we're looking for. Bum, 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 bum. So, whenever we combine two reactions together, we take their equilibrium constants and we multiply them together. So our overall Keq of this reaction is going to be equal to this 1/15 times 2. So we're just multiplying this value and this value together, which leaves us with our answer, which is Keq equals 0.13. So this question asks, which of the following statements about equilibrium is false? Statement A says when Keq is greater than 1, that means that at equilibrium we have more products and less reactants. I'm trying to draw this being smaller here to show that the numerator is larger than the denominator. And indeed, that's true. Because if Keq is greater than 1, that means the product-to-reactant ratio at equilibrium is going to have more products and fewer reactants. So this statement I like. We're going to give this a check. Statement B, when Keq is less than Q, so if Keq is less than Q, this says the reaction shifts left to reach equilibrium. So let's think about what this tells us. So Q is the product-to-reactant ratio that we have. Keq, on the other hand, is the product-to-reactant ratio is trying to get to. So Keq is where the reaction is going. So if Q, the product-to-reactant ratio that we have, is greater than Keq, the product-to-reactant ratio that the reaction is trying to get to, that means that we would need more reactants. We have too many products at this point, so the reaction would have to go to the left in order to make more reactants to get to equilibrium. So statement B, no, I like this too. If K is less than Q, that means we need more reactants, so the reaction would shift left to reach equilibrium. Statement C, delta G equals 0 at equilibrium. That is absolutely true. At equilibrium, the reaction is not proceeding forward nor in the reverse direction. Spontaneously, delta G equals 0. We're at an energy minima. All is well. This is a true statement. Statement D, catalysts do not change the quantity of products produced. Also true. Catalysts do not change that ideal product-to-reactant ratio. They do not change the equilibrium constant. They just let us get to equilibrium more quickly by lowering activation energy. So this is absolutely true. And then finally, adding a noble gas to the reaction vessel will always shift the reaction to the right. That's just a silly statement that involves science words. That's not true at all, even though it has science words in it. So this is the false one, choice E. In this question, we're looking at this reaction of taking ammonium chloride and dissolving it in water in an aqueous solution. So we're given some information here. You wouldn't be expected to look at a reaction of something dissolving and go, ooh, that looks endothermic or exothermic. But we're given some pretty hard evidence here where we're told that the temperature read from the thermometer drops from 23 degrees Celsius to 10 degrees Celsius. So the surroundings are getting colder. Remember, the thermometers read surroundings. And if the surroundings are getting colder, it means one of two things. Either dementors, lol, not going to be the answer in a chemistry problem, or an endothermic reaction. Because this reaction is stealing heat from the environment, it's changing that heat into chemical potential energy. But if it's causing the temperature to drop, that means that we're looking at an endothermic reaction. So we have a positive delta H for this reaction. Now then, looking at our reaction, we're going from a mole of solid to 2 moles of products, and the products are aqueous. So whenever we dissolve something, solids have the least inherent entropy. Aqueous, far more. They can move more about in their aqueous environment. So in terms of entropy, this is a positive delta S. So we have a positive delta H and a positive delta S. And now we need to figure out, so we can eliminate actually most of these choices. So we're left between B and E. So is this spontaneous at low temperatures or high temperatures? In order to think about this, let's consider the equation. Delta G equals delta H minus T delta S. So let's consider the implications of the fact that it's an endothermic reaction that leads to an increase in entropy and see how that would affect delta G. And in order to do this, I like to think of two extremes. So extreme 1 is going to be at a very low temperature. So let's say at point, lots of zeros, 1K. Basically absolute zero. Delta G will be equal to delta H. This term is not affected by the magnitude of temperature. So this is going to be a positive value. And at this ridiculously low temperature, if T is really small, it's going to turn this whole T delta S parameter into something very, very small, practically zero. So I'm going to put minus and I'm going to make a really little positive sign here, because what we would have at low temperatures is a positive number minus a positive number, a very, 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 very small positive number. If you take a positive number and you subtract from it a number that is also positive but smaller in magnitude, what are you going to end up with? Well, this is going to end up being positive, which means a non-spontaneous reaction at low temperatures. So let's think of situation 2. And yes, we've technically answered the question at this point, but it doesn't hurt to go through and analyze what would happen at large temperatures. So at high temperatures, let's say 1 billion Kelvin, then delta G is going to equal delta H, which again is not affected by temperature, so this is going to be some positive value, minus, and if the temperature is really large and delta S is positive, that means it's going to be a positive number minus a positive number, a very, 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 very large positive number. So if we have a positive value for delta H, and we're subtracting a really ridiculously positive value for our T delta S, we're going to end up with a negative delta G, which means that at high temperatures, this would be spontaneous. Now, what differentiates a small, or like a low temperature from a high temperature? That's different for any given reaction or any given phase change. We would actually need thermodynamic data about the enthalpy and entropy to figure out what separates the two. But this type of qualitative analysis will allow us to definitively say that this reaction is going to be spontaneous only at high temperatures and non-spontaneous at low temperatures. All right, this particular problem is pretty similar, in fact, very, very, very similar to a homework problem. And we're given 2 atmospheres of a whole bunch of things, CO2, H2O, and CO. And we're trying to see what the equilibrium partial pressure is going to be of water. So if we're given initial amounts, which is what we're given up here, and we're trying to find equilibrium amounts, that means when in doubt, ice it out. We're going to need to use an ICE table to figure out this problem. So let's do just that. We're going to write out ICE next to our table. Classic. So ICE. And then our initial amounts of everything going to be, we're told that everything is 2 atmospheres. So this is 2 atmospheres, and this is 2 atmospheres, and this is 2 atmospheres, and this is 2 atmospheres. All right, now then, which way will the reaction go? And you could technically calculate Q versus K in order to figure this out. That will always tell you which way a reaction is going to go. In fact, you know what? Heck, let's do it. So Q is going to be equal to products over reactants. So the pressure of H2O times the pressure of CO over the pressure of H2 times the pressure of CO2, which would be equal to 2 times 2, or 2 squared, over 2 times 2, which is 2 squared, which would be 1. That works. So if we compare Q versus K, what number is larger? So Q, the product to reactant ratio that we have, 1 is greater than K, the product to reactant ratio that we want, which is 0.770. So Q is greater than K, which means this reaction has too many products as it is and needs to go to the left. So that means that our change is going to be negative for everything on the product side and positive for everything on the reactant side. The other way that we could think about this is that the fact that K is equal to 0.770 tells us that reactants are favored at equilibrium. If reactants are favored at equilibrium and we have an equal amount of everything, aka the situation that we have, 2 atmospheres of everything, the only way to get to equilibrium is to make more reactants, because it's not a 50-50 ratio. That would be a Keq of 1. So we could also think about this from that perspective. Also, if you mismatch the signs in your change line, you can still technically get the right answer. It's just not telling you really, truly which way the reaction is going. So we know that the reaction is going to the left. Let's work with that. So it's a 1-to-1-to-1-to-1 ratio of everything. So it's going to be plus x minus x minus x, which will leave us at equilibrium with 2 minus x, 2 minus x. Oh, nope, sorry. 2 plus x. That's how math works. 2 plus x, 2 minus x, and 2 minus x. Now we're going to write everything into our equilibrium expression. At this point, we are halfway there. So Keq is going to be equal to the pressures of products. So pressure of H2O times the pressure of CO divided by pressure of H2 over reactants, so pressure of CO2. So now let's plug in our values and solve and see what we end up getting. Keq, we're told, is 0.770. And that's going to be equal to our products, which are 2 minus x and 2 minus x. So it's going to be 2 minus x squared over reactants, which are both 2 plus x. So 2 plus x times 2 plus x is going to be 2 plus x squared. Now, you will never have to use the quadratic formula in Chem 112. There's always going to be a way of simplifying these equilibrium expressions. So what I'm going to do is take the square root of both sides here. That'll make our lives a lot easier. Let's see what we get. we get 0.877 is equal to 2 minus x over 2 plus x. At this point, we're just a few algebraic steps away from our answer. So I'm going to multiply this 2 minus x through, and what we'll have then is that 0.877 times, actually I'm going to give myself a little bit more room here. We're going to have it 0.877 times 2 plus x is equal to 2 minus x. We have a few options moving forward. I'm just going to factor this through to these. And what we'll get is 1.754 plus 0.877x is equal to 2 minus x. So I'm going to subtract the 1.754 from both sides, and I'm going to add x to both sides, and we'll get 1.877x is equal to 0.246. And then all we have to do is divide both sides by the 1.877. And we'll end up getting x is equal to 0.131. The last thing we need to do is make sure that we're actually answering the question that's given. So the question is asking for the equilibrium pressure of water vapor, of H2O. So H2O's pressure is going to be 2 minus x. So the pressure of H2O will be equal to 2 minus the 0.131, which is equal to 1.869 atmospheres, which rounds to 1.87 atm. This question asks which of these following sets of parameters are true when a reaction is non-spontaneous as written. So if a reaction is non-spontaneous as written, that means we're looking at a positive delta G, and we're looking at Q being greater than K, because the product-to-reactant ratio that we have, Q, is greater than K, the product-to-reactant ratio that we want. So let's see which of these match up with that. Statement A, delta G is positive and Q is greater than K. Hey, that's it. That's the one. In this question, we're given the Kp of this reaction, and we're asked to find, so we're given the pressures of NOBr and of NO. Well, we're told that they're equal, and we're asked to find the equilibrium pressure of Br2. So first things first, let's write an equilibrium expression for this reaction. The Kp is going to be equal to the pressure of products to their respective coefficients. So pressure of nitric oxide squared times the pressure of Br2 over reactants. So the pressure of NOBr squared. Now, we're also told here that NOBr, which is this, well, that's equal to the partial pressure of NO. So actually, this is going to make our lives a lot easier, because if those two are equal, then if we square them both, they're still equal. And if we divide one square by the other, that means, well, guess what? These cancel out. If they're the same value, they're going to cancel out, which means that in this situation, Kp is equal to the pressure of bromine. So this makes our job pretty easy, because we're given Kp, which is 0.416. That is our answer. And we're done.